All right, let's start. So I understand that last time Umesh talked about random variables and expectations. So today we'll talk about linearity of expectation. So that's a property of averages that makes computing expectations of random variables much easier than just working out of the definition. Then we'll see various examples of how to compute expectations of random variables. And then we'll talk about independence of random variables. And then we look at variance. So with all those notions in place, then it will be possible, and probably this will happen in the next lecture when Umesh is back, to do calculations of the form, if I have a random variable and I know the expectation, how likely it is that when I measure the random variable, I see a value much bigger or much smaller than the expectation. So you'll see a series of results that say, under certain conditions, random variables tend to almost always be very close to the expectation. So if, say, a random variable is the running time of an algorithm on random inputs, if you compute the expectation of that random variable, now you know the average running time of your algorithm. But you still don't know if that's usually the running time, or maybe with some small probability the algorithm takes a very long time, and with high probability takes a much shorter time. If you're also able to compute the variance, then if that's small, you'll be able to say things like not only the average running time is this much, but almost surely it will be not much more and not much less. So that's how you can argue that quicksort with a fixed pivot on random inputs takes on average times order of n log n, but also never much more than order of n log n, except with very small probability. Okay. So the linearity of expectation is the following result that says that if x and y are two random variables, then the expectation of their sum is equal to the sum of the expectations. Okay. So before looking at the proof, there is a way to visualize what this identity means. So let's say your sample space is picking 3 random bits. So it will be all sequences of 3 bits. And your probability is uniform. And let's say you have a random variable which is the sum of the first 2 bits. And let's say y is the sum of the last 2 bits. So you can just completely describe what is going on for x, y, and x plus y for every outcome of your sample space. So there are 8 possible outcomes. I say x will be 0, 1, 1, 2, 1, 2. Sorry, first 2 bits, so it will be 1, 1. 0, 0, 1, 1, 1, 1, 2, 2. And y will be 0, 1, 1, 2, 0, 1, 1, 2. All right, so the sum will be whatever. 3, 1, 2, 3, 4. Now, how do you compute the expectation of a random variable? You add up each possibility in the sample space, and then for that possibility, you add up the value of the random variable times its probability. In this case, all the 8 outcomes have probability 1/8, so the expectation of x is just the sum of all those possibilities divided by 8, so it will be 1. And the same for y. The expectation of y is the sum over, so in general, the expectation of a random variable is the sum over the outcomes in your sample space of the probability of the outcome times the value of the random variable for that outcome. So in the case, all those probabilities are 1/8, so you just sum the values of x. In which case it's 8, in this case also 8. And in the case if you add them up, it will be 16. But so you can see that the expectation of x plus y is what you get by, for every outcome, adding up x and y, and then adding up the results. So it's just the sum of all the numbers that are in this square. If you compute the expectation of x, you're just adding up the numbers in this column. And if you compute the expectation of y, you're adding up the number in this column. So if you then add them up those numbers with each other, you're still just adding up whatever is in this 2/8 table. So the reason why linearity of expectation holds is just that when you compute the expectation of x plus y, or the expectation of x plus the expectation of y, you're just adding up the same values, be adding up by row instead of adding them up by column, but you get the same result. So let me just rewrite the same argument formally. So we want to get a formula for the expectation of x plus y. So we just apply the formula for the expectation to the random variable x plus y. So this will be the sum over all the outcomes in the sample space of the probability of that outcome times the value of the random variable for that outcome. So that will be x for omega plus y for omega. Then you just distribute the sum. And so that's just the expectation of x plus the expectation of y. So if you apply this rule inductively, you also get that if x1, xn are random variables, the expectation of their sum is going to be equal to the sum of their expectations. So here is a. So there are many cases where calculations about expectations are greatly simplified by using this rule. In fact, one reason why expectations is an important quantity related to random variables is the simplicity in computing it compared to other quantities like the median that doesn't satisfy linearity like the expectation does. Okay. So here is one example that I think you have seen the other time. So let's say that your probability space is n coin tosses of a coin that has bias p. So a coin that comes up heads with probability p and tails with probability 1 minus p each time. And let's call S the number of heads in these n coin tosses. So if you apply the definition of expectation to compute what is the expectation of S, so then you're going to say, well, it's going to be the sum over all possible values that the random variable can take, which is from 0 to n, but 0 will not contribute, of k, which is the value, times the probability that the random variable has value k. And that's p to the k, 1 minus p to the k, and choose k. So last time, Umesh gave you a series of tricks to come up with the fact that this expression is n times p. But if you didn't know or couldn't see those tricks, that's a really difficult summation to get an understanding of. But here is how you can use linearity of expectation to come up with this result without knowing anything, like hardly with any calculation. So you can say, so let's write S as a sum of random variables, x1 plus x2 plus xn, where xi is the random variable defined as 1 if the ith coin comes up heads, and 0 otherwise. These are well-defined random variables. For every outcome of your coin tosses, this is a numerical value associated with that outcome. And it's also true that S is the sum of these random variables, because each xi is 1 if the ith coin is heads. So the number of heads will be the sum of these xi's. The heads contribute 1, the tails contribute 0. So by linearity of expectation, the expectation of S is going to be equal to the summation over I of the expectation of xi. So now we have reduced the task of computing one expectation to the task of computing n expectations. But now those expectations are really simple, because what is the expectation of xi? Well, we have to look at what are the possible values that xi can take, and then add up that value times the probability that it comes up. So this will be 0 with probability 1 minus p, and 1 with probability p. And those are the only values that this random variable can take. So this expectation is p. So that means the expectation of S is the summation of n numbers. Each of them is p. And so this is n times p. Right, so this is a completely calculation-free argument. All you need to say is that if I have a random variable that is 1 with probability p and 0 with probability 1 minus p, the expectation is p, which is like a one-line argument. Okay? Yeah. Any questions about this calculation? Okay. So I'll show you a couple more examples of distribution of random variables that have very complicated distribution, but you can compute their expectation in a really simple way. Okay, let's move here. Right, suppose that n homeworks are returned randomly to n students. And let's call R the number of students that receive their own homework. That's going to be there. 400 of you submit your 400 homeworks. And then we email back the results completely at random. So everybody gets the homework of a random person. So how many students would get their own? So there's a way to make this question a little bit more abstract. So what's happening? So what is a way to model the sample space of this experiment? So an element of the sample space is defined by a permutation of 1 through n into 1 through n. Every permutation is a possible outcome of this randomized experiment. And the permutation models the problem by saying that if the outcome of this experiment is the function f, that means that student I receives the homework of student f of I. And this is uniform, so each f has probability one over the size of the sample space. Right? So how many permutations of the numbers 1 through n through 1 to n are there? Right. So each one will have probability 1 over n factorial. So now what is R? So that a function models an outcome of the experiment by saying that if the experiment is described by permutation f, f of I is the student that gets the homework of student I. So R is counting for how many i's f of I is equal to I. So we are picking a random permutation, and we're asking, our random variable is the number of fixed points of a random permutation. So as you can imagine, it's not too difficult, but it's a bit complicated to come up with the description of the distribution of R. Like, what is the probability that random permutation has 0 fixed points, 1 fixed point, 2 fixed points, and so on. You can write those probabilities, and you can add them up. Then you could try to find some trick to evaluate that sum. But instead, it's much easier to compute the expectation of R by writing again R as a sum of simpler random variables, and then computing the expectation of each of them. And in fact, every time you have a random variable that's counting something in the outcome of your sample space, and you want to compute the expectation, it almost always works to define 0, 1 random variables, where each random variable is 1 if something needs to be counted and 0 otherwise. So we're going to write R as x1 plus x2 plus xn, where xi is 1 if the ith student gets his homework back, and it's 0 otherwise. So now if we want to compute the expectation of R, we just need to figure out the expectations of those random variables. The expectation of a 0, 1 random variable is just the probability that it's 1. All right, so if you pick a random permutation, what do you think is of n inputs into n outputs? What do you think is the probability that, let's say, f of 1 is equal to 1? It should be 1 over n, right? Because the permutation is random, so it doesn't prefer any element to any other element. So for every I, the value of f of I is equally likely to be any number from 1 through n. Another way to see that this intuition is correct is just to apply the definition. So your sample space is of size n factorial, and now you are counting all the permutations that map I to I, and then map the other n minus 1 elements in any possible way. Right? So that's just like one such permutation is essentially a permutation of n minus 1 elements. It's a 1-on-1 correspondence. So there are n minus 1 factorial permutations that fix f of I equal I. And in fact, this ratio is exactly 1 over n. So now the expression of R, so this is true for every I. So this implies that the expectation of R is n times 1 over n, so it's 1. So I don't know if that would have been intuitive just from the description of the experiment. But this expectation is the same regardless of how big is your set that you're picking a random permutation over. The result is independent of n. All right, let me show you one more example. This is what I'm showing now is something that relates to analysis of hash functions for set-type data structures. This is the simplest question you can ask about this kind of setup. So suppose you have n balls. and you have n bins. And then you randomly throw balls into bins. So each ball independently has probability 1 over n of ending up in any of the bins. So the choices are independent for every ball. So that means that your sample space is the set of all the functions now from 1 through n into 1 through n. Not just permutations. And the probability of any such function is 1 over n to the n, the number of possible choices. So these models, when you have a hash table that has as many entries as the number of elements that you want to hash, each one is hashed randomly, so the balls would correspond to the data items that you want to hash. The bins would correspond to the entries of the table. This random process would correspond to how the hash function maps data items to hash table locations. And so there are many questions that are interesting about this process, such as typically how full is the fullest bin, because that will give you the worst case performance of the hash table for that setup. Or you could ask how many bins end up empty, because that's wasted space in the data structure. So since that's easier to compute, that's what we're going to look at. So let's call, I don't know, U for unused, the number of empty bins. So I don't know if you have an intuition for what's going to end up happening. There are as many balls as bins. So if the assignment was careful, instead of being random, you could just put one ball in every bin. No bin would be empty. Instead, things are completely random, but still, somehow a random assignment should be pretty spread out. So I don't know if you have a sense of whether the number of empty bins should be something like order of n, order of root n, order of log n. So let's do the calculation and see what comes out. So we can write U as, at this point it's really mechanical. You write it as a sum, you are counting something, so you want to write your random variable as a sum of 0, 1 random variables. And so UI is going to be the random variable that is 1 if the ith bin is empty, and it's 0 otherwise. And so we just have to compute the probability that UI is 1, probability of getting an empty bin. So what is this probability that the ith bin ends up empty? Well, this is an end of event. So it's the probability that the first ball does not end up in I, and the second ball doesn't end up in I, and the nth ball does not. So we are choosing where to put the balls independently. So the probability of, so all those events are independent, which means that this will just be the product of the probabilities. Let's call it B. All right, so now we are just focusing on one ball and one bin. So we said each ball is thrown randomly, which means each ball is probably 1 over n of ending up in any of the possible bins. So not going into bin I means that it has n minus 1 other possibilities for where to end up out of n possibilities. So each of those probabilities is n minus 1 divided by n, and then we need to multiply them together. So this means that the probability that UI is 1 is going to be the product for B going from 1 through n of that probability of not B not going into I, which we said is n minus 1 divided by n. So this is the product of this number by itself n times. So that's the exact formula. For every n, it will be a different number. But for large n, this is roughly 1 over e. And already for n is a few hundreds, it's very close to 1 over e. So that's like, I don't know, 30%, 35%. So that's the probability that a particular bin remains empty. And so that's the expectation of one of the UIs. The expectation of U will be the sum of this. So the expectation of U will be the sum of all these expectations. So it will be n times this. So it will be roughly n divided by e. And so if you have a hash table with as many items as table entries, and the hash function is completely random, you might expect a constant fraction of table entries to go empty, roughly 35% of them to go empty. Now, of course, you also want to know what usually happens. Like, is it always close to 1 over e? Is it usually much bigger or much smaller? But that's something you'll be able to compute after we talk about variance of random variables. Okay, so that's the general lesson. When you have a random variable that is counting something and you want to compute its expectation, write your random variable as a sum of 0, 1 random variables, and now you're just down to computing pretty simple probabilities and adding them up. So there is a related property that sometimes comes up. There's also that for every constant c, the expectation of c times x is the same as c times the expectation of x. That's even easier to prove, because when you write down this expectation, there's just going to be a c in every term. You can pull it out, and you're going to get c times the expectation. Okay. All right, so now that we have the... so the expectation is one number that we can associate with random variables, and tells us something about how big it usually is. So if x is, say, the running time of an algorithm on random inputs, the expectation, which will be the average running time, is already something very useful to know. But something that is also important is to know whether almost always the random variable is close to the expectation, or if it's possible that sometimes it's much bigger and sometimes it's much smaller. So in general, we would like to understand how big is this difference of a random variable minus its expectation. Now, that's again a random variable. Our interest is in whether this is usually small or often big. And now something you can do when you have a random variable that you are interested in is compute its expectation. That will give you a ballpark of how big your random variable usually is. But it turns out that computing the expectation of this difference, because of the absolute value, I mean, sometimes it's possible, but it's very messy. It doesn't lead you to easy calculations, except in special cases. So the simple but really powerful trick is that to study how much random variable deviates from its expectation, instead of looking at the absolute value of the difference, you look at the square of the difference. That sort of qualitatively, it's the same. This random variable will be big if and only in the cases in which x deviates from the average. But since there is no more absolute value, now it becomes a differentiable function. It has lots of really nice properties. It's much easier to study. And the expectation of this quantity, which tells you, typically how much bigger or how much smaller is x of the expectation if you square that value. So this is called the variance of the random variable. Yeah? So because you are looking at the square of this difference, you would expect something like the square of the variance to tell you roughly how much more or how much less is your random variable compared to its expectation. And in fact, that's the square root of this is an important quantity. The standard deviation of x is the square root of the variance. This is a definition. So next time you'll see Chebyshev's inequality that says that with high probability, a random variable is no more than a constant times the standard deviation away from its expectation. So a small standard deviation is telling you that your random variable tends to be pretty concentrated around the average. All right, now let's see if you can compute this quantity in a few interesting cases. So that once you have Chebyshev's inequality, you know how to figure out concentration on the average for a few interesting cases. Okay. So first, it's so first it's helpful to look at a slight simplification of the formula. So let's actually, first of all, let's just give a name to the expectation. We'll call it mu. That's just to save on typing. So the variance of x, we said by definition, is the expectation of the deviation from the average squared. Well, let's expand the square. So this will be the expectation. Well, also, let's use the notation that we just introduced. Keep in mind, x is a random variable, mu is a number. It's just the expectation of x. Yeah. So x is a function of the sample space, mu is just a number. Okay, so just expanding the square. But now we can use linearity of expectation. And so this will be the expectation of x squared minus 2 mu, recall mu is a constant, you can pull it out, times the expectation of x, plus the expectation of mu square. Now, mu square is a number. The expectation of a number is just a number. And now one more observation is that, okay, so what is the expectation of x? We just call it mu. So this term here, minus 2 mu expectation of x, is just minus 2 mu square plus mu square. So you just have the expectation of x squared minus mu square. So so that in some cases simplifies the calculation of the variance a bit, because we just need to study what is the expectation of the random variable x squared, which is the same as x except every variable is squared, and then compute the expectation of x and square it. Also, since the variance is the expectation of a random variable that is always non-negative, because a square is always non-negative, so that means that the variance is always greater than or equal to 0. But we just computed that it's the expectation of x squared minus mu squared. So this means that if you have a random variable and you look at what is the expectation of its square, that's always bigger than or equal to what you get if you compute the expectation of the random variable and then square the result. So that's a special case of the Cauchy-Schwarz inequality. There are many cases where this is useful to know. Now let's see a couple of simple properties of this quantity. Our goal before the end of class will be to compute what's the variance of the number of heads when you have n coin tosses of a biased coin. Because if you just write down the expression for it, it's really complicated. But we'll see a series of properties of variance which will make the calculation very simple. All right, so one property is that if C is a constant, so it's a real number, then the variance of C times x is going to be C squared times the variance of x. So if you double a random variable, its variance will quadruple. So that makes sense because the actual measure of how much random variable deviates from the expectation is the square root of the variance. And the square root of the variance scales with the linearly with C. So why is this true? Well, we can use that expression that says and so you can use linearity of expectation here and pull this C square out. And use linearity of expectation here to pull the C out and then pull it out of the square. So that's C squared times the variance of X. So that's what happens if you multiply a random variable by a constant. But if you add or subtract a constant from a random variable, what do you think happens to the variance? Well, maybe here it's easier to look at the original definition. So according to the first definition, the variance of X plus C is, you look at what is the difference between X plus C and its average and square that. That's a new random variable, and you compute the expectation of that. But then you can use linearity of expectation here, and so this is just the expectation of X plus the expectation of C, but the expectation of a constant is just the constant itself. So this becomes the expectation of X plus C minus the expectation of X minus C. So that's just X minus the expectation of X. So that's the same as the variance of X. So if you add a constant to a random variable, you change its expectation, but you don't change its variance. And this should be intuitive because if you have, maybe X is a random variable that tends to concentrate around this value. So when you take multiple samples, it will be sometimes smaller and sometimes bigger, but always in a pretty small range. So then X plus C will be the same random variable, but when you sample it, it will tend to look like the same interval, just shifted. Now, the variance is something that is telling you how much you deviate from the expectation. So it's only something that's about differences between values of the random variable. If you add a constant to the random variable, that will just always cancel out and will not change how the variable tends to be close or not close to its expected value. But that's just the algebra of it. So what about the variance of X plus Y? Well, it turns out that the there is no, actually there is a simple formula, but it's not just a simple formula of the variance of x and the variance of y. It really depends whether this will be much bigger when x and y are correlated and smaller when x and y are independent. So what we will prove and what will help us compute lots of variances of useful random variables is the following fact. Let's go to a lemma. That if x and y are independent random variables, then the variance of x plus y the same as the variance of x plus the variance of y. To see that some kind of condition is necessary to have this linearity, we can just go back to what we proved before, that the variance of a constant times x is the constant squared times the variance of x. So if I ask you, what is the variance of x plus x? Well, this is the same as the variance of 2 times x, which is 4 times the variance of x, which is not 2 times the variance of x. So it's not true that for arbitrary pairs of random variables, when you add them up, the variance will add up. In fact, it could end up being much bigger than that. But when the random variables are independent, then this happens, which is a very important fact. All right, so you have seen independence of events. I'm not sure you've seen independence of random variables. So let me define that. Then we'll come back and prove that lemma. So this will be a definition. We're going to say that x and y are independent So what the definition will capture is that we want to say the two random variables are independent if every event about the value of x is independent of every event about the value of y. So two events are independent if the probability of happening together is the product of the probabilities. So what we want to say here is that those two are independent if for every two values a and b, the probability that x equals a and y equals b is the same as the product of the probabilities. So you haven't seen conditional probabilities yet, but some way to think of that is that if I tell, you get an outcome from your sample space. This outcome defines the value of x and y. And if x and y are independent, the fact that I tell you what is the value of y is not telling you anything about what is the value of x. So that will have the same distribution as if I didn't know y. But formally, this is what it is. The probability of x having some value and y having some value is precisely the same as the product of the probabilities. Now, an example of two random variables that are not independent is the first example we defined when we talked about linearity of expectation. Let's say in my sample space, I pick 3 random bits in an unbiased way. So each one is probably 1/8. And then x is the sum of the first 2 bits, y is the sum of the last 2 bits. So let's say omega is 0, 1 cube. Probability distribution is uniform. X is sum of the bits, the first 2 bits, and y is the sum of the last 2 bits. Well, those are random variables that are not independent. So intuitively, the reason is that they both depend on the second bit. So if I tell you y, I'm telling you something that you wouldn't have known otherwise about x. But we can just see it formally according to that definition. That let's say the probability that x is equal to 2 and y is equal to 2. Actually, maybe it's more dramatic if we look at probably that x is equal to 2 and y is equal to 0. All right, so this probability is 0 because if the sum of the first 2 bits is 2, that means that both of the first 2 bits are 1. And so y cannot be 0 because the second bit has to be 1. But the probability that x is 2 is a quarter. And the probability that y is 0 is also a quarter. So if x and y were independent, this probably would have to be 1/16. But instead it's 0, so they're not independent. But let's say when we were looking at that random variable s over there, so we take n coin tosses or fair coin, we count how many heads we get. We said that this random variable could be written as x1 plus x2 plus xn, where xi is a 0, 1 random variable that is 1 when xi comes up heads. Now, those random variables, any two of them are independent because you can just sort of write down what are the 4 possible outcomes. They will each have probability either p squared, 1 minus p squared, or p times 1 minus p. And they will be precisely the product of the probabilities. So those would be an example of random variables that are independent. Okay, so that's the definition of independence. It's something that may or may not happen for random variables depending on how they're defined. And here's a very useful property of independence. that if x and y are independent, then the expectation of x times y is the product of the expectations. This is not true in general. You can have pairs of random variables that are not independent, and this equation fails. Also, it's possible this equation is true for random variables that are not independent. But what this lemma is saying is that a sufficient condition for this very useful identity to hold is that the two random variables be independent. And the proof is just rearranging the sums. So what is the expectation of x times y? Well, we need to look at all possible values that the product x times y can take, and what are the probabilities that those values are taken. So to enumerate all possible values that x times y can take, we can enumerate all values that x can take, all values that y can take, and then in that case we have a term. In that case, x times y will be equal to a times b, and so that will be that term of our sum. Right, so we are summing over possibilities in the sample space that the random variable x times y has a certain value times the probability that this happens. Now, the condition of independence says that this is the same as the summation over a and b of the product of these probabilities. So now I just need to rearrange the sums, and what you get is the summation over a probability that x equal a times a times summation over b probability y equal b times b. So you get the expectation of x times the expectation of y. All right, so now we have enough pieces to prove this lemma. Right, so first of all, it will be convenient to work with random variables whose expectation is 0. So let's define x bar to be the random variable which is just x minus the expectation of x. And let's define y bar to be y minus the expectation of y. So now x bar is just like x, except that we subtracted a number, a fixed constant. And y bar is the same as y, except that we subtracted a fixed number. And one thing we said was that when you add or subtract a fixed number to a random variable, you don't change its expectation. Sorry, you don't change its variance. You change its expectation, but not the variance. So the variance of x bar is the same as the variance of x. And the variance of y bar is the same as the variance of y. And in fact, if I look at x plus y, that's the same as x bar plus y bar up to subtracting a constant. So the same is true the same is true here. The variance of x plus y is the same as the variance of x bar plus y bar. Okay. Let's compute the variance of x bar plus y bar. So this is the expectation of x bar plus y bar squared minus the square of the expectation. But the expectation of x bar plus y bar is just 0. If you compute the expectation of x bar, you just get expectation of x minus expectation of x. And same for y bar. So this term really doesn't exist. So we just need to understand what is the expectation of this square. Okay, so we can expand the square and apply linearity of expectation. So this will be the expectation of x bar squared plus twice the expectation of x bar y bar plus the expectation of y bar squared. So far, this is true for every random variable, x and y. This is a formula for the variance of the sum of two random variables that always works. But now we're going to use the assumption that x and y are independent. So if x and y are independent, x bar and y bar are also independent, because the event that x bar has a certain value is just the same as the event that x has that value plus the expectation of x. So here, the expectation of the product of x bar and y bar can be written as the product of the expectations. Yeah, but what is the expectation of x bar? We computed it before. It's like expectation of x minus expectation of x, so just 0. The same for y. So this part also goes away. But now, the expectation of x bar squared is just the variance of x bar. And the expectation of y bar squared is just the variance of y bar. Because the definition of variance, a definition of variance is the expectation of the square minus the square of the expectation. But as we have already used twice, the expectation of x is 0. So the expression for its variance is just the expectation of the square. Right, but then we said that x and x bar have the same expectation, y and y the same variance, y and y bar have the same variance. So this is the variance of x plus the variance of y. So indeed, by using in this step the independence of x and y, and hence the independence of x bar and y bar, we proved that the variance of x plus y is the same as the variance of x plus the variance of y. So now this takes us to our first non-trivial calculation of variance, which is that we're going to compute the variance of the number of heads in n-biased coin tosses. Any questions about this derivation? So just the same basic facts about x versus x bar used over and over. All right, here is our random variable s, the number of heads when we do n coin tosses independently. Each of the n coins is going to come up heads with probability p and tails with probability 1 minus p. So what is the variance of S? Well, if we just apply the definition, is the expectation of S minus its expectation all squared. So it's going to be the summation over k of the difference between S and its expectation times the probability that this is the difference between S and its expectation. Yep. So there are some tricks to take this really messy summation and coming up with its value. But we're going to, again, do a pretty much calculation-free derivation by using what we have understood about the variance of independent random variables. Yeah, so we have written S as a sum of n random variables. Those are all pairwise independent and also mutually independent. So we can apply that lemma and say that the variance of S is going to be equal to the summation for I going from 1 through n of the variance of xi. So now what we need to understand is the variance of a really simple random variable. It's a random variable that can take only value 0 or 1, takes value 1 with probability p, value 0 with probability 1 minus p. So for that, that's simple enough that we can just apply the definition. Right, so what is the variance of xi? So one of the definitions is expectation of xi squared minus the square of the expectation. So we know the expectation of xi, we computed it before, it's p, because xi is p is 1 with p and 0 otherwise. So this is p squared. All right, so what about the expectation of xi squared? What are the possible values of xi squared? They're just 0 and 1. So xi can be 0 or 1, And so xi squared can be 0 squared or 1 squared. In fact, xi squared is precisely the same random variable as xi. And so this expectation is just p. So the variance of xi is p minus p squared. So the variance of S is just n times that. So this really messy expression, we really know calculation, we figured it out. It's np minus np squared. Okay. It's not impossible to really manipulate the sum until this comes out, but it's pretty hard. Now here are a couple of things we can observe from this calculation. One, as maybe we would expect, is that the variance is 0 only when either p is 0 or p is 1. In fact, those are when you do a sequence of biased coin tosses, the only case where there is no variance in the outcome, where the outcome is always what you would expect, is when there is no randomness in the outcome. And those are the cases p equals 0, where everything comes out tails, and p equals 1, where everything comes out heads. In all other cases, there is the possibility of moving away from the expectation, and this is reflected in a non-zero variance. But the other thing to see is that the variance is order of n which means that the standard deviation is order of square root of n. So when you do n coin tosses, your expectation of the number of heads would be n times p, but as you will see next time from Chavichel's inequality, it will be not much more than np plus root n, and not much less than np minus root n. And for large n, that's a very tight characterization. And you can also see the difference with, let's look at a variable s prime, which is the number of heads when you pick one coin with that probability heads probability p and tails probability 1 minus p, and then you copy it n times. And so in this other experiment, which is over a different sample space, S prime is going to be n with probability p and 0 with probability 1 minus p. Now the expectation of S prime and S is the same. But the variance is very different. Because basically S prime is just n times x1. And before we did the calculation that if you multiply a random variable by a constant, the variance scales as the square of that constant. So the variance of S prime is going to be not n times p minus p squared, but it's going to be n squared times that. Anyway, you could still see S prime as the sum of n01 random variables. The one tells what is the outcome of the ith bit. And that's why the expectations give you the same value. But in the case of S, you write S as the sum of n independent 0,1 random variables. And then the variance scales linearly in n. But S prime is a sum of highly dependent, in fact, identical random variables. And there the variance scales like n squared. Okay. All right, so I guess next time we're going to see how, once you know that the variance of S is order of n, you can see how S is always very close to its expectation.